Reliable Messaging Unveiled, the Inbox and Outbox Patterns. Chapter 1, Introduction, the Challenge of Distributed Systems. The modern digital landscape is defined by its ceaseless motion. From the instant gratification of online shopping to the intricate dance of financial markets, our lives are interwoven with software systems that must operate continuously, flawlessly, and at scale. For decades, the preferred architectural style for such systems was the monolith, a single, sprawling application encompassing all functionalities. It was a simpler time in many respects, where all components shared the same memory space, the same database, and the same deployment unit. However, as business demands for agility, speed, and independent innovation grew, the monolithic approach began to show its cracks. Deploying even a minor change to one part of the system often required redeploying the entire application, which slowed down release cycles and increased the risk of introducing new bugs. Scaling one busy part of the system meant scaling the entire monolith, often an inefficient use of resources. Furthermore, large, undifferentiated codebases made it difficult for independent teams to work without stepping on each other's toes, leading to bottlenecks and reduced team autonomy. This growing friction led to the significant architectural shift towards distributed systems, most notably in the form of microservices. Imagine dismantling a monolithic application into a collection of smaller, independent services, each responsible for a specific, well-defined business capability. Each microservice typically manages its own data store, a database, a cache, or a file system, and communicates with other services over a network. Each is deployable and scalable independently. This architectural transformation promised considerable benefits. Increased agility, improved resilience, as the failure of one service ideally doesn't bring down the entire system, independent scaling, and the flexibility to use different technologies where appropriate. But with newfound flexibility came a fresh set of formidable challenges. The elegant simplicity of in-process calls, shared memory, and single database transactions vanished. Now, services reside on different machines, communicating over a network that, by its very nature, is unpredictable and unreliable. This shift ushered in a new era of problems unique to distributed environments. The inherent nature of distributed systems. When moving from a single application to a network of communicating services, developers often fall prey to what are known as the fallacies of distributed computing. These are common, yet false, assumptions that lead to fundamental design flaws. For instance, we might assume the network is always reliable, or that latency is negligible, or that bandwidth is infinite, or that the network is always secure, or that topology never changes, or that there is a single administrator, or that transport costs are zero, or that the network is homogeneous. In reality, the network is none of these things. The reality of distributed computing involves partial failures. In a monolith, it's generally all or nothing. The application either works or it doesn't. In a distributed system, one service can fail while others continue to operate normally. This creates a much more complex failure landscape, where coordinating actions across services becomes a non-trivial problem. No global state. There is no shared memory or a single, consistent clock across dispersed services. Each service maintains its own view of the world, and there is no simple way to achieve a truly global, real-time snapshot of the entire system state. This makes coordination, especially around business transactions, incredibly challenging. Unreliable network. Messages can be lost, duplicated, delayed, or delivered out of order. Network partitions can occur, isolating parts of the system from each other. These are not edge cases, they are fundamental properties of communication over a network. The problem of state and communication. Consider the seemingly straightforward act of placing an order on an e-commerce website. In a monolithic world, this might involve a single atomic database transaction that updates the order status, deducts inventory, and records the payment. All these operations happen within the same transactional boundary, ensuring that if any part fails, the entire operation is rolled back, leaving the system in a consistent state. In a distributed microservices environment, however, this single logical action unfolds across several independent services. The order service handles the order creation and updates its database. It then needs to inform the inventory service to deduct stock, the payment service to process the payment, and the shipping service to prepare for dispatch. These informations typically take the form of messages sent asynchronously over a message broker. What if the inventory service is temporarily unavailable? What if the message informing the payment service gets lost? What if the network fails midway through the process, after the order service has committed its data, but before the message could be reliably sent? These scenarios lead to inconsistencies. An order might be placed without inventory being reserved, or a payment processed without an order ever being confirmed in the system. Traditional distributed transactions, like the infamous two-phase commit, 2PC, exist to solve this very problem. However, in modern microservices architectures, 2PC is largely avoided due to its high overhead, complexity, and the fact that it tightly couples services, making them less robust to network failures and introducing a single point of failure, the transaction coordinator. The need for reliability, why it matters. The ability to successfully complete business processes, end-to-end, even when multiple services are involved and failures occur, is paramount. Businesses cannot afford data inconsistencies. An order goes through, but the stock isn't reduced, leading to overselling. Lost business. A customer places an order, but a message fails to arrive, and their order never gets fulfilled. Reputational damage. Systems behave erratically, leading to customer frustration and loss of trust. Operational headaches. Debugging complex, multi-service workflows where messages might be missing or duplicated is a nightmare, draining engineering resources. The fundamental question then becomes, how do we guarantee that business processes spanning multiple services are completed correctly and consistently, even if failures occur at any point, without resorting to the complexities and pitfalls of traditional distributed transactions? This is the domain of reliable messaging. It demands a mechanism that can bridge the critical gap between a service's local database transaction and the reliable delivery of external messages. What this book will cover. This book aims to demystify how to achieve this crucial reliability. We will show you that the problem of guaranteeing atomicity across a local database transaction and an external message send can be robustly solved by adopting two powerful, yet often misunderstood, architectural patterns: the outbox pattern and the inbox pattern. We will embark on a comprehensive journey, starting with the very problem we've outlined, the fundamental challenges of distributed communication and the inherent atomicity gap. We will then dissect these critical patterns in detail, exploring their core mechanics, various implementation strategies, from simple database polling to advanced change data capture techniques, and how they ensure that messages are reliably sent and reliably processed. We will cover practical considerations like performance, scalability, monitoring, idempotence, and error handling. Finally, we'll examine real-world applications, discuss common pitfalls, and contrast these patterns with related architectural approaches. By the end of this book, you will have a deep understanding of the inbox and outbox patterns, equipping you with the knowledge and confidence to build truly resilient, consistent, and trustworthy distributed systems. Let's begin by diving deeper into the specific perils that plague asynchronous communication. Chapter 2. The Perils of Asynchronous Communication. In the previous chapter, we established that distributed systems, particularly those built with microservices, fundamentally rely on communication across networks, while synchronous communication, like direct HTTP requests, has its place. Many interactions within a distributed architecture are best handled asynchronously. The promise and power of asynchronous systems. Asynchronous communication, often facilitated by message queues or event buses, such as Apache Kafka, RabbitMQ, Amazon SQS, or Azure Service Bus, offers a powerful set of benefits. Decoupling. Services no longer need to know about each other's direct network addresses or be simultaneously available. They simply publish messages to a broker, and other interested services can subscribe to them later. This reduces direct dependencies and makes services more independent. Increased responsiveness. A service can publish a message and immediately return a response to the caller, without waiting for downstream services to process the request. This is crucial for user-facing applications where low latency is critical. Higher throughput and scalability. Message brokers can buffer messages, allowing producers to send messages at a higher rate than consumers can process them. Consumers can be scaled independently, adding more instances to handle increased load, drawing from the message queue. Resilience and reliability. If a consumer service goes down, messages aren't lost. They remain in the queue until the service recovers. Retry mechanisms can be implemented at the broker or consumer level, providing a robust layer against transient failures. Enabling event-driven architectures. Asynchronous communication is the backbone of event-driven systems, where services react to events, e.g., order placed, payment approved, generated by other parts of the system. This fosters a reactive and highly responsive overall architecture. These advantages are so compelling that asynchronous messaging has become a cornerstone of modern distributed system design. However, reaping these benefits comes with its own set of significant challenges. Common pitfalls of asynchronous messaging. While message queues offer robust delivery guarantees, they don't solve all problems inherent in distributed communication. The very nature of asynchronous interactions introduces complexities that must be carefully managed. 2.2.1 Message loss. Despite the best efforts of message brokers, messages can still be lost. This can occur for several reasons. Producer failure before publish. A service generates a message but crashes before it can successfully publish the message to the broker. The business action might already have been committed to the service's internal database, e.g., an order saved, but no one downstream is ever notified. Broker unavailability. If the message broker is temporarily unavailable or experiences a partition, a producer might fail to send its message. If the producer doesn't have a robust retry mechanism or cannot store the message locally for later transmission, the message effectively disappears. Network issues. A network glitch could cause a message to be dropped between the producer and the broker, or between the broker and the consumer. Consumer failure before acknowledgement. A consumer receives a message, processes it, but then fails before it can acknowledge that the message has been successfully processed to the broker. If the broker is designed to only remove messages upon acknowledgement, this might not technically be lost, but it leads to reprocessing. However, if the acknowledgement is assumed, the message might be considered processed when it wasn't. Lost messages can lead to severe data inconsistencies. Imagine an order-placed message that never reaches the inventory system. The customer has paid, but their item is never reserved, leading to potential overselling and customer dissatisfaction. 2.2.2 Duplicate messages. The opposite problem, duplicate messages, is equally insidious. Duplication often arises from retry mechanisms, which are themselves crucial for reliability or from network uncertainties. Producer retries. A producer sends a message to the broker but doesn't receive an acknowledgement. Assuming the message failed, it retries sending it. Unbeknownst to the producer, the first message might have actually reached the broker successfully, but its acknowledgement got lost on the way back. Now, the broker has two identical messages. Consumer retries due to lack of acknowledgement. A consumer processes a message, but fails to send an acknowledgement to the broker due to a network issue or its own crash. The broker, not having received confirmation, might redeliver the message to another consumer instance, or the same instance upon recovery. Broker failures. In rare cases, a message broker's internal replication or fault tolerance mechanisms might lead to unintended message duplication during recovery from failure. The impact of duplicate messages can be severe, especially in transactional contexts. Consider a payment system. If an apply payment message is processed twice, the customer might be double charged. Or an add inventory message processed multiple times could lead to inflated stock counts. This double charging problem is a classic example of where simply relying on message broker guarantees isn't sufficient for business-level consistency. 2.2.3 Out-of-order messages. While many message brokers support ordered message delivery within a single partition or for messages with the same key, Ensuring global order across all messages or across partitions is complex and often not guaranteed by default. This can be problematic in scenarios where the sequence of events is critical. An account-activated message arrives after an account-deactivated message, leading to an incorrect account state. A price update. $10 message arrives after a price update. $5 message, even if $5 was the earlier, correct update. If consumers process messages purely based on arrival order, inconsistencies can arise. 2.2.4 Network partitions and latency. Distributed systems operate over networks, and networks are inherently unreliable. Partitions can split a system into isolated segments, preventing services from communicating. High latency can delay messages, making real-time coordination difficult. These conditions exacerbate the problems of message loss, duplication, and ordering. 2.2.5 Consumer failures. Even if a message flawlessly reaches the consumer might fail during processing. What happens to the message? Most message brokers have dead letter queues, DLQs, for messages that repeatedly fail processing. Consumers also need robust error handling strategies that decide whether to retry a message, discard it, or move it to a DLQ. The atomicity gap. Database transaction versus message send. All these pitfalls converge on one fundamental and critical problem in distributed systems: the atomicity gap. This refers to the inherent difficulty in ensuring that a local database transaction and an external message send are treated as a single, atomic operation. Let's illustrate with a common scenario: a service that creates a new customer. To do this, it needs to store the new customer's data in its local database, notify other services that a new customer has been created by sending a customer-created message to a message broker. A naive approach would be: begin database transaction, insert into customer's values, commit database transaction. Now try to send the message. Send customer-created, message to broker. What could go wrong with this seemingly logical sequence? Scenario 1. Database commit succeeds, message send fails. The customer data is successfully saved in the database. But then, just as the service tries to send the customer-created message, the message broker goes down, or a network problem occurs, or the service itself crashes. The message never gets sent. Now, the customer exists in the database, but no other service, e.g., the CRM, marketing, analytics, knows about them. This leads to data inconsistency and a broken business process. Scenario 2. Message send succeeds, database commit fails. This scenario is less common with the order above, but if the order were reversed, or if the database commit itself failed after the insert but before the commit, the problem would be evident. More subtle, if the database commit appears to succeed but is rolled back later due to a crash, yet the message was sent. Now, downstream services might be processing a customer-created message for a customer that doesn't actually exist in the source system. This creates phantom data or processing of non-existent events. Scenario 3. Ghost messages on failure. Even if the sequence is send, message, then commit DB, what if the message sends successfully, but the database commit fails? Or the service crashes right after sending? The message is out in the world, triggering downstream actions, but the originating service's state is incorrect. The core issue is that a local database transaction, which guarantees atomicity within that database, and an external network operation, like sending a message, fundamentally operate on different systems and cannot be atomically linked by conventional means. We cannot have a single, distributed transaction that spans the database and the message broker without incurring significant performance penalties and tight coupling, resembling the very problems that led us away from monoliths and eschewing 2PC. This atomicity gap is not just an academic concern. It's a critical vulnerability that can lead to data loss, inconsistent states, and broken business processes in real-world distributed systems. To build robust, reliable, and consistent distributed applications, we absolutely must bridge this gap. This is precisely where the inbox and outbox patterns come into play. They offer an elegant, robust solution to this fundamental problem, ensuring that messages are reliably sent and processed, without relying on complex and often undesirable distributed transactions. In the next chapter, we will begin to explore how these patterns solve this core challenge. Chapter 3, Atomic Operations, the core problem. In the previous chapter, we dissected the seductive promises of asynchronous communication and quickly exposed its inherent perils. From message loss and duplication to out-of-order delivery, these issues underscore a single, glaring vulnerability: the atomicity gap between local database transactions and external message sending. Now, we'll dive deeper into why this gap is so problematic and why conventional solutions often fall short in the context of modern distributed systems. 3.1. The definition of atomicity in a distributed context. In database theory, an atomic operation is one that is indivisible and irreducible. It either completes entirely or doesn't execute at all, leaving the system's state unchanged. Databases achieve this through transactions, ensuring ACID properties, atomicity, consistency, isolation, durability. When you update a customer record and simultaneously decrease an inventory count in a single database, the database's transactional guarantees ensure that both operations succeed or both fail, preventing inconsistencies. In a distributed system, the concept of atomicity becomes far more complex. If one microservice updates its own database and then needs to notify another microservice about this change through a message, these two distinct actions, database write and message send, are not inherently atomic. They are susceptible to independent failures, leading to the atomicity gap we described. We want business atomicity, the guarantee that a logical unit of work, spanning multiple services via message passing, either fully completes across all involved systems or has no lasting effect. 3.2. Why simple retries and idempotents are insufficient on their own. Before we introduce Inbox and Outbox, it's worth exploring why simpler approaches fail to fully address the atomicity gap. 3.2.1 Retries, a double-edged sword. Retries are essential in distributed systems. When an operation fails due to a transient network glitch or a temporary service unavailability, retrying it often leads to success. Message brokers incorporate retries into their delivery mechanisms, and robust clients implement exponential backoff and jitter for retrying failed sends. However, retries alone don't solve the atomicity gap. If a producer commits to its database but loses connection before successfully sending the message, retrying the send is fine, but it doesn't roll back the database change. Conversely, if the message sends but the database commit fails, retrying the database commit won't remove the already sent message from the broker. Retries address network unreliability, but not the fundamental transactional boundary problem. Furthermore, aggressive retries can exacerbate the issue of duplicate messages. If a message is sent successfully, but the acknowledgement (ACK) from the broker is lost, the producer might retry, leading to two identical messages delivered to the broker and potentially processed multiple times by consumers. This brings us to idempotence. 3.2.2 Idempotence, handling duplicates after the fact. An operation is idempotent if performing it multiple times has the same effect as performing it once. For example, set x to 5 is idempotent. Add 5 to x is not. In distributed systems, designing operations to be idempotent is crucial, especially because message duplication is a fact of life. Consider the double charging problem. If a payment service processes a charge customer message, it should be designed such that if the exact same message arrives again, e.g., identifiable by a unique transaction ID included in the message payload, it doesn't charge the customer a second time. It performs the check, realizes the charge has already occurred, and simply acknowledges the message without further action. While idempotence is a powerful defense against the consequences of duplicate messages, it operates after the fact. It prevents undesirable side effects once a duplicate message has already been received. It doesn't prevent the duplicate message from being sent, nor does it close the atomicity gap where the crucial decision point lies: how to atomically commit local state and initiate the external message send. Idempotence is necessary but not sufficient. It's a critical mechanism for consumers, but it doesn't solve the producer's problem of reliably sending messages that are tied to local transactions. 3.3 Why traditional distributed transactions, e.g., two-phase commit, are often avoided. Given the atomicity problem, why not just use traditional distributed transaction coordinators and protocols like two-phase commit, 2PC? How 2PC works briefly. In a 2PC protocol, there's a coordinator and multiple participants, e.g., databases, message queues. Prepare phase. The coordinator sends a prepare message to all participants. Each participant then prepares its operations, e.g., records changes in a log, locks resources, and responds that it's ready to commit or aborts. Commit phase. If all participants respond, ready, the coordinator sends a commit message. Each participant then makes its changes permanent. If any participant responds abort, the coordinator sends a rollback message to everyone. Why 2PC is generally avoided in microservices. Performance bottleneck. The prepare and commit phases involve multiple network round trips and durable writes to transaction logs. This introduces significant latency. Locks held during the prepare phase reduce concurrency, especially if a participant is slow. Single point of failure. The coordinator is a central point of failure. If it crashes during the commit phase, some participants might have committed while others are still waiting, leading to inconsistencies that require complex manual recovery. Tight coupling. Services involved in a 2PC protocol become tightly coupled at runtime. If one participant is unavailable or slow, the entire distributed transaction is blocked. This goes against the core microservice principle of independent deployability and failure isolation. Resource management. Databases and message brokers need built-in support for 2PC, and integrating them reliably can be complex. Scalability challenges. As the number of participants grows, the coordination overhead increases, making it difficult to scale. In essence, 2PC forces a strong, synchronous consistency across disparate systems, sacrificing the very benefits that microservices and asynchronous communication aim to deliver. Loose coupling, independent scalability, and high availability. It is often seen as an anti-pattern in cloud-native, highly distributed architectures. 3.4 The need for a different approach. The challenges of asynchronous communication, coupled with the drawbacks of traditional distributed transactions, lead us to a fundamental conclusion. We need a mechanism that can bridge the atomicity gap without resorting to the heavy machinery of 2PC. We need a way to ensure that a local database transaction is guaranteed to be linked to an external message transmission. Messages are reliably delivered at least once. Downstream consumers can handle, at least once, delivery safely, i.e., gracefully handle duplicates. This is precisely the set of problems that the Inbox and Outbox patterns were designed to solve. They bring the concept of transactional atomicity from the realm of the single database into the distributed world, but not by enforcing a global transaction. Instead, they achieve this by cleverly leveraging the atomicity of a local database transaction. They allow a service to first guarantee its own state change and the intent to send a message within its own transactional boundary, and then asynchronously ensure that the message is eventually sent. In the next two chapters, we will unravel the mechanics of these two powerful patterns, starting with the Outbox pattern, which tackles the crucial problem of guaranteeing message delivery from the producer side. Chapter 4. Introducing the Outbox pattern, guaranteeing message delivery. In the previous chapters, we highlighted the critical atomicity gap, the challenge of ensuring that a local database transaction and an external message send are treated as a single, indivisible operation. We also discussed why traditional distributed transactions like two-phase, commit, are generally ill-suited for modern, highly elastic microservices architectures. This brings us to the Outbox pattern, a widely adopted and robust solution for guaranteeing message delivery from a service while maintaining transactional integrity. 4.1 The core problem revisited. The atomicity gap. Before deep diving into the Outbox pattern, let's briefly recap the problem it solves. Imagine an order service. When a customer places an order, the service needs to persist the order details to its database, publish an order-placed message to a message broker so that other services, e.g., inventory, payment, shipping, can react. If the order service attempts to do these two things as separate steps, first commit to the database, then send the message, it faces the transactional risk. Database commit succeeds, message send fails, the order is recorded but no other service is notified. Inventory might not be reserved, payment not processed, and shipping never initiated. The system is in an inconsistent state from a business perspective. Message send succeeds, database commit fails, or system crashes before commit. A message is published to the world about an order that doesn't actually exist in the order service's database. Downstream services might waste resources processing a phantom order. The outbox pattern aims to bridge this gap by making the act of intending to send a message an atomic part of the local database transaction. 4.2 What is the outbox pattern? The outbox pattern solves the atomicity gap by ensuring that the writing of business data to a database and the recording of an outgoing message are part of a single, atomic database transaction. It works by introducing an outbox table within the producer service's own database. Here's the fundamental workflow: transactional write to outbox table. When a service needs to publish a message following a business operation, e.g., creating an order, it performs two writes within a single local database transaction. It persists the business entity's data, e.g., the order record, to its primary table. It simultaneously inserts a record representing the message to be sent, e.g., order placed event, with relevant payload, destination, and metadata into a dedicated outbox table. Atomic commit. Both the business data write and the outbox table insert are committed or rolled back together. This ensures that either both succeed or neither do. There is no state where the business data is saved, but the intent to send the message is lost, or vice versa. Asynchronous relaying. A separate, independent component, often called the message relayer or outbox relayer, then monitors this outbox table. This relayer is responsible for reading messages from the outbox table, publishing these messages to the actual external message broker, e.g., Kafka, RabbitMQ. Once a message is successfully published to the broker, marking the corresponding entry in the outbox table as sent or deleting it to avoid resending. Key principle: the outbox pattern decouples the act of preparing a message for sending, which is atomic with the business transaction, from the act of actually sending the message externally. The local database becomes the temporary, durable queue for outgoing messages. 4.3 Benefits of the outbox pattern. Guaranteed message delivery, at least once. Since the message is durably stored in the database within the same transaction as the business data, we are guaranteed that if the business operation succeeds, the message will eventually be sent. This effectively eliminates message loss from the producer's side. Transactional consistency. The business data and the intention to send the message are always consistent. There's no scenario where an order is saved without a corresponding event queued for sending, or vice versa. Avoids distributed transactions. The entire process relies solely on the atomicity of a single, local database transaction. There is no need for two PC or similar complex distributed coordination protocols. This preserves the loose coupling and independent deployability of microservices. Resilience to broker downtime. If the message broker is temporarily unavailable, the producer service can continue to operate normally as long as its database is available. Messages simply accumulate in the outbox table, and the relayer will pick them up once the broker recovers. Simpler business logic. The application's core business logic only needs to concern itself with writing to its database and the outbox table. It doesn't need to handle complex message broker acknowledgements or retry logic directly for outgoing messages. 4.4 How the outbox relayer works. Conceptual. The outbox relayer component is crucial to the pattern's success. There are two primary strategies for implementing the relayer. 4.4.1 Polling the outbox table. This is the most straightforward approach. The relayer application, which could be a separate microservice, a background process within the producer service, or a serverless function, periodically queries the outbox table for new, unsent messages. Workflow, poll interval. The relayer wakes up every n seconds, e.g., 1 second. Read messages. It queries the outbox table for messages that have not yet been sent. It's crucial to select messages in an ordered fashion, e.g., by insertion timestamp or an auto-incrementing ID to preserve the order of events. Publish to broker. For each selected message, the relayer attempts to publish it to the external message broker. Mark as sent delete. Once a message is successfully published to the broker, the relayer marks that message in the outbox table as sent, e.g., by setting a send timestamp or status flag, or deletes the entry. This operation should itself be transactional to avoid resending if the relayer crashes between publishing and marking. A common pattern is to delete the record in the same transaction as fetching the next batch. Considerations for polling. Latency. The message delivery latency is influenced by the polling interval. Frequent polling reduces latency but increases database load. Database load. Constant polling can put a strain on the database, especially with high message volumes. Concurrency. Multiple relayer instances can be run for scalability, but they must coordinate to avoid sending the same message twice, e.g., by using select. 4. Update skip locked or unique message IDs with broker-level duplicate detection. 4.4.2 Change data capture, CDC. A more advanced and often more efficient approach for high-volume scenarios is to use change data capture, CDC. Instead of actively polling the database, CDC mechanisms listen to the database's transaction log, also known as the write-ahead log or WAL. This is the underlying mechanism databases use for replication and recovery. Workflow Database Log Listener. A CDC tool, e.g., Debezium Apache Flink with database connectors, acts as a listener to the database's transaction log. Event stream. When the producer service performs a transaction, inserting into its business table and the outbox table, this change is recorded in the transaction log. The CDC tool captures these changes as a stream of events. Filter and publish. The CDC tool filters these events, identifying inserts into the outbox table. It then extracts the message payload and metadata from the outbox table entries and publishes them directly to the external message broker. Benefits of CDC: near real-time delivery. Messages are captured and published almost instantly as they are committed to the database, significantly reducing delivery latency compared to polling. Reduced database load. The database is not actively polled, reducing query load. Scalability. CDC tools are often designed for high throughput and can scale independently of the application. Considerations for CDC: complexity. CDC setup and management are generally more complex than simple polling. It requires integrating with database-specific log mechanisms. Database support. Not all databases expose their transaction logs in an easily consumable format for CDC tools. Operational overhead. Requires running and maintaining a separate CDC infrastructure. Regardless of the relayer implementation, the core guarantee remains. The message is durably stored with the business transaction before it leaves the local system, thus bridging the atomicity gap. 4.5. Designing the outbox table. A typical outbox table schema might include id, unique identifier for the message, e.g. UUID, occurrence, timestamp when the event occurred in the system. Type. The type of event message, e.g., order placed, product updated. Aggregata type. The type of the business entity involved, e.g., order, customer. Aggregated. The ID of the business entity, e.g., orderid. Useful for traceability and consumer processing strategies. Payload. The actual message content, usually in JSON or Avro format. Correlationid. For tracing across distributed systems. Tracid. Another common tracing identifier. Status. Optional for polling, pending, sent, failed, can be used by relayer. Processed birellurat. Timestamp when the relayer successfully processed it for soft deletes or auditing. The id should be used as a globally unique identifier for the message. This is critically important for the consumer side to enable idempotence, which we will discuss in Chapter 5. 4.6 Challenges and considerations. While powerful, the outbox pattern is not without its considerations. Duplicate relaying. As with any distributed system, the relayer attempting to publish messages to the broker might retry if it doesn't get an ACK. This can lead to duplicate messages being sent to the broker. This is expected and the consumer's responsibility to handle via idempotence. Order guarantees. While messages are inserted into the outbox table in the order of their business transactions, maintaining strict global message order through the message broker and to all consumers can still be challenging, depending on the broker's capabilities and consumer scaling. Usually, order is guaranteed per aggregate, e.g., all messages related to ordered, 123 are ordered. Database scalability. The outbox table can grow very large in high-volume systems. Strategies for partitioning, archiving, and periodic cleanup are necessary to prevent it from becoming a bottleneck. Increased latency, polling. As noted, polling introduces some latency depending on the interval. Relayer complexity. Building a robust, fault-tolerant relayer, especially for CDC-based approaches, requires careful design, monitoring, and operational effort. Despite these challenges, the outbox pattern remains the most widely accepted and reliable method for bridging the atomicity gap from the producer side. It allows services to confidently commit their internal state changes and know that the corresponding messages will eventually propagate throughout the system. Now that we understand how the outbox pattern guarantees that messages are sent, the next crucial step is to understand how consumer services can reliably handle these messages, ensuring correctness even in the face of potential duplicates, and ensuring their own downstream processes are atomic. This leads us to the inbox pattern, which we will explore in the next chapter. Chapter 5, Introducing the Inbox Pattern, Handling Idempotence and Duplication. In Chapter 4, we explored the outbox pattern, a robust mechanism for ensuring that messages are reliably sent from a producer service, making the act of messaging atomic with local database operations. However, reliable message delivery to the message broker is only half the battle. Once messages arrive at the consumer service, new challenges emerge. What if the same message is delivered multiple times? What if the consumer crashes mid-processing? How can a consumer guarantee that its own reaction to a message is atomic and does not lead to inconsistencies? This is where the inbox pattern comes in. The inbox pattern is designed for the consumer side of asynchronous communication. Its primary purpose is to ensure that a consumer processes each message exactly once from a business perspective, even if the message broker, or the outbox relayer, delivers it multiple times. It achieves this by combining local transactional integrity with a robust duplication detection mechanism. 5.1 The Consumer's Dilemma, At Least Once Delivery. Modern message brokers typically guarantee at least once delivery. This means you are assured that a message will eventually be delivered to the consumer at least one time. However, due to network retries, consumer crashes, or even specifics of the outbox relayer, it is entirely possible and often probable that a message will be delivered more than once. Consider a charge customer message from a payment service. If a consumer receives this message multiple times and processes it naively each time, the customer could be double charged. Or, if an update inventory message indicating stock deduction is processed twice, the inventory count could become negative, leading to stock discrepancies. This is why at least once delivery immediately necessitates exactly once processing from the business logic standpoint. The inbox pattern provides a systematic approach for a consumer service to achieve exactly once processing semantics without complex distributed transactions. 5.2 What is the inbox pattern? The inbox pattern, similar to the outbox, leverages a dedicated table within the consumer's own database, the inbox table. This table serves as a durable log of all messages that the consumer has successfully received and is processing or has processed. Here's the fundamental workflow. Receive message. A consumer service receives a message from the message broker. Transactional write to inbox table and business logic. Before processing the message's business logic, the consumer attempts to perform two writes within a single, local database transaction. It inserts a record representing the newly received message, including its unique message ID, this is crucial, into its inbox table. It executes the business logic that results from processing the message, e.g., updating its local domain model, creating a new record, etc. Atomic commit and duplication check. Attempted insert. The insert into the inbox table uses the message's unique id, e.g., set by the producer's outbox pattern as a primary key or unique index. If the message has already been received and processed, i.e., an entry with that id already exists, the insert will fail due to a primary key or unique constraint violation. Transactional outcome. If the unique ID is new, both the inbox table insert and the business logic execution are committed together. If the inbox insert fails, meaning it's a duplicate message, the entire transaction is rolled back and the business logic is not executed again. Acknowledge to broker. Only after the local database transaction, including the inbox table insert and business logic, successfully commits, the consumer acknowledges the message to the message broker. This tells the broker that the message has been durably processed and can be removed from the queue or marked as consumed. Key principle. The inbox pattern ties the durability of message receipt and the execution of business logic into a single, local database transaction. The inbox table acts as a guard against reprocessing duplicate messages and as a log of successfully processed messages. 5.3 Benefits of the inbox pattern. Exactly once processing from a business perspective. This is the primary benefit. By using the unique message ID to deduplicate, the consumer ensures that the side effects of processing a message, e.g., charging a customer, updating inventory, only occur once, even if the message is delivered multiple times. Transactional consistency on the consumer side. The consumer's local state changes caused by processing a message are atomic with the acknowledgement of that message. There's no scenario where the business logic is applied, but the message is lost to the source broker or vice versa. Resilience to consumer crashes. If the consumer crashes after receiving a message, but before its local transaction commits, the message broker will eventually redeliver the message, because it wasn't acknowledged. When the consumer recovers, it will attempt to process the message again. But the inbox pattern will prevent reprocessing the business logic if it had already been successfully committed before the crash. If it hadn't been committed, the transaction would roll back, and the second attempt would succeed. Loose coupling with broker. The consumer's processing logic is not tightly coupled to specific broker guarantees. It relies on the broker providing at least once delivery, which is a common and robust guarantee. Auditing and traceability. The inbox table serves as a durable log of every message processed, making it easier to audit and trace events through the system if needed. 5.4 Designing the inbox table. A typical inbox table schema might include message aid, the unique ID of the message, typically provided by the producer, e.g., from its outbox table. This column should be the primary key or have a unique index to enforce the exactly once processing guarantee. Receive it at timestamp when the message was received by the consumer. Type. The type of event message, e.g., order placed, product updated. Payload. The actual message content, usually in JSON format. Process it at timestamp when the message was successfully processed and its transaction committed. Processing status. Optional can track the status like received, processing, completed, failed. Correlationed for tracing across distributed systems. Tracid, another common tracing identifier. The message aid is the cornerstone of this pattern. It's usually a UUID or another globally unique identifier generated by the producer service, often when it writes to its outbox table. 5.5 How the inbox pattern works in practice. Example. Let's trace a charge customer message from a payment service producer to a billing service consumer. Payment service producer implements outbox. Customer initiates payment. Payment service opens a database transaction. It updates customer payment status in its own database. It inserts charge customer message with a unique message aid, e.g., UUID ABC123 into its outbox table. Transaction commits. Payment services outbox relayer publishes UUID ABC123 message to the broker. Billing service consumer implements inbox. Billing service receives UUID ABC123 message from message broker. Attempt 1. Billing service opens a database transaction. It tries to insert a record with message aid UUID ABC123 into its inbox table. Assuming no prior entry, this succeeds. It proceeds to execute business logic. Update customer account set balance equals balance charge amount. The transaction commits successfully. The billing service acknowledges UUID ABC123 to the message broker. Scenario: consumer crashes after commit, but before ACK. Broker redelivers UUID ABC123 later. Attempt 2, due to redelivery. Billing service receives UUID ABC123 message again. It opens a database transaction. It tries to insert a record with message aid UUID ABC123 into its inbox table. This insert fails due to a unique constraint violation, because UUID ABC123 is already in the inbox table from attempt 1. The entire transaction rolls back, including any potential side effects of the business logic. No double charge occurs. The billing service will still acknowledge UUID ABC123 to the message broker. As it's already processed, state is now known, preventing further redeliveries from the broker. 5.6 Challenges and considerations. Idempotence is key. The success of the inbox pattern hinges on the message aid being truly unique across all messages and on the database correctly enforcing the unique constraint. Database scalability. The inbox table can grow very large, similar to the outbox table. Strategies for archiving and periodic cleanup are necessary. Cleanup. As messages accumulate, old entries in the outbox and inbox tables might need to be cleaned up. This requires careful consideration of retention policies and potential uses for auditing or replaying events. Order guarantees. While the inbox handles duplication, it doesn't inherently guarantee specific message ordering beyond what the broker provides. If strict ordered processing of all messages is required, additional mechanisms, like processing messages using a single logical thread per partition queue, may be necessary, or the application might need to implement internal reordering buffers. However, typically, idempotence and guaranteed at least once is sufficient. Transactional granularity. It's important that the business logic associated with a message is contained within the same transaction as the inbox table write. If the business logic itself involves external calls, e.g., to another service or an external API, that part of the processing won't be atomic with the inbox record. For such scenarios, the saga pattern, Chapter 9, or other eventual consistency mechanisms might be required. The inbox pattern, when combined with the outbox pattern, forms a powerful duo for achieving reliably sending messages outbox and reliably processing them inbox in distributed systems. It provides robust guarantees for data consistency and exactly once processing from a business perspective, all while preserving the benefits of loose coupling and independent scalability inherent in microservices architectures. In the next chapter, we will delve into the practicalities of implementing these patterns with real-world examples and code snippets. Chapter 6. Implementing the patterns. Practical considerations. Having explored the theoretical underpinnings and benefits of the outbox and inbox patterns, it's time to delve into their practical implementation. This chapter will provide concrete examples and discuss the various choices and trade-offs involved in bringing these patterns to life in your distributed systems. 6.1 General Implementation Principles. Before diving into code, let's establish some universal principles for implementing both patterns. Language agnostic. The core concepts of inbox and outbox apply regardless of the programming language, Java, C#, Python, Go, Node.js, etc., or database, PostgreSQL, MySQL, SQL Server, MongoDB, Cassandra, etc., you are using. The examples here will use conceptual pseudocode that can be easily translated. Database as the source of truth. Both patterns fundamentally rely on the transactional guarantees of your local application database. This database is the central point of coordination for ensuring atomicity. Unique message IDS. Every message flowing through the outbox and inbox must have a globally unique identifier. UUIDs are ideal. This is indispensable for deduplication and traceability. Idempotency is a prerequisite. While the inbox pattern handles duplicate detection, the underlying business logic that consumes messages should also be designed to be idempotent where possible. This provides a layered defense against inconsistencies. 6.2. Implementing the outbox pattern. The two main implementation choices for the outbox pattern revolve around how the messages are relayed from the outbox table to the message broker. Polling or change data capture, CDC. 6.2.1 Outbox implementation with polling. This is arguably the simpler and more common approach to start with, especially for moderate message volumes. Step 1. Application logic, producer service. The core application code needs to perform the business operation and insert the message into the outbox table within a single database transaction. Conceptual pseudocode. Inside your order service place order details, method. Begin transaction. 1. Persist business data. Order equals new order, details. Order repository save, order. 2. Create message for outbox. Message outbox equals new outbox message. Id generates UID. Occurred at now. Type order placed. Aggregate type order. Aggregated ordered. Payload serialized to JSON order. Outbox repository save message outbox. Commit transaction. Important, do not send message to broker here directly. The relayer will handle it. Step 2. Designing the outbox table. Create table outbox messages. Id UUID primary key. Occurred at timestamp with time zone default CURR. Type varchar 255 not null. Aggregata type varchar 255 not null. Aggregated varchar 255 not null. Payload JSONB not null. Or text for simpler cases. Process edit timestamp with time zone. Marks when message relayer processed it. Unique id. Ensure message id is unique. Optional index for efficient fetching by relayer. Create index outbox message processed at on outbox messages. Process edit where process edit is null. Create index outbox message occurred at on outbox messages occurred at. The process edit column is crucial for identifying messages that need to be sent and for marking them as processed. Step 3. Implementing the polling message relayer. This is typically a separate application or background service. Conceptual pseudocode. Message relayer service runs continuously. Loop indefinitely. Try. Messages equals outbox repository find unprocessed messages limit 100 order by. Occurred at ASC. If messages is empty, wait for polling interval ms, e.g. 500 ms. Continue. For each message in messages. Publish success equals message broker publish. Message type, message payload, messaged, message.correlationed. If publish success, update the message status in the outbox table. This should also be part of a transaction if you're marking multiple messages, but for a single message it's often fine. Outbox repository mark is processed, message ID now. Else, log error, potentially retry later, or use dead letter mechanism. Loaderer, failed to publish message. Plus messaged, optionally, update message status to pending error to indicate a retry is needed. Or simply let it be picked up in the next loop if not marked processed. Catch exception as e. Loaderer, error in message relayer loop, plus e-message. Wait for error backoff ms, e.g. 5000 ms. Relayer considerations, concurrency. If you run multiple relayer instances, ensure they don't process the same message twice. This can be achieved by distributed lock, using a distributed lock, e.g. Redis Zookeeper, to ensure only one relayer is active. SQL 4 update skip locked. For some databases, like PostgreSQL, you can use select 4 update skip locked to allow multiple readers to skip rows already locked by other transactions. Atomic updates. When marking a message as processed, use update, where id equals, and process edit is null to ensure only one relayer marks it. Cleanup. Implement a background job that periodically sweeps the outbox messages table, deleting or archiving messages older than a certain duration, e.g., 7 days that have been successfully processed at. 6.2.2 Outbox implementation with change data capture, CDC. CDC tools like Debezium or Apache Flink with Kafka Connect offer a more sophisticated and less invasive way to implement the outbox pattern. especially for high-volume systems that demand near real-time messaging. Step 1. Application Logic Producer Service. The application code remains exactly the same as with polling. It simply inserts into the Outbox Messages table within its business transaction. Step 2. Designing the Outbox table. Same as for polling. Step 3. Configuring the CDC tool. This is where the magic happens with CDC. You configure a CDC connector specific to your database, e.g., Debezium Kafka connector for PostgreSQL. Conceptual configuration, simplified. Debezium connector configuration for PostgreSQL. Connector class equals eo.debezium.connector PostgreSQL Postgres connector. Tasks max equals 1. Database hostname equals yordpost. Database port equals 5432. Database.user equals Debezium user. Database password equals Debezium password. Database DB name equals your database. Database.server.name equals myappdb server. Schema whitelist equals public. Table whitelist equals public outbox messages. Publication auto create mode equals all tables. Slot.name equals Debezium slot. Plugin.name equals pig output. Transforms equals extract payload. Transforms extract payload type equals eo.debezium transforms extract. New record state. Transforms extract payload drop tombstones equals false. Transforms extract payload add fields equals op. Source TSMS. Transforms.extract payload.delete handling mode equals rewrite. Message.key.columns equals public outbox messages, id. Topic prefix equals myapp events. This configuration tells Debezium to connect to your PostgreSQL database, monitor the public outbox messages table, capture new insert events, transform them into a normalized JSON payload, and publish them to a Kafka topic named myapp events public outbox messages, or similar, based on prefix and table name. Step 4. Kafka topic or other message broker. The CDC tool will automatically publish messages to a Kafka topic. These messages will reflect the structure of your Outbox Messages table. Step 5. Consumer integration, optional for CDC. While the inbox pattern is still needed for duplicates, with CDC, you often don't need a process edit column in the Outbox table, as CDC streams the change as it happens and doesn't need to mark it. The message is considered processed once it hits Kafka. CDC considerations, operational complexity, requires deeper understanding of your database's WAL and the CDC tool itself. Ecosystem integration works best if you are already using a message broker like Kafka, which has strong CDC tool support. Near real-time, excellent for low-latency messaging. Less database strain. Minimal impact on the application database as it simply reads the transaction log. 6.3. Implementing the inbox pattern. The inbox pattern is implemented directly within the consumer services application logic and database. Step 1. Designing the inbox table. Create table inbox messages. MessageAid UUID primary key. The unique ID from the producer's outbox message. Receive it at timestamp with time zone default CURRENTTMSTMP. Type varchar 255. Not null, payload JSONB not null, process edit timestamp with time zone, correlationed varchar 255, traced varchar 255. Unique MessageAid. This is crucial for deduplication. Optional, index for auditing or specific queries. Create index Inbox message receive it at on inbox messages receive it at. Step 2. Consumer service logic. When the consumer service receives a message from its subscribed queue topic, it processes it in a single database transaction. Conceptual pseudocode. Inside your inventory service handle order placed, message received message, method. MessageId equals received message get correlationed. Assuming producer's outbox message ID is in correlation ID. Message type equals received message get type. Message payload equals received message get payload. Begin transaction. Try. 1. Try to record message in inbox table. Inbox message equals new inbox message. MessageId. Received at now. Type message type. Payload. Message payload. Inbox repository save. Inbox message. This will throw error if MessageId already exists. 2. Execute business logic. Applies only if save above succeeded. Order equals deserialize from JSON message payload. Perform inventory deduction, e.g. Inventory repository.deduct stock, order.producted, order quantity. Update inbox messages with process edit timestamp on successful business logic. Inbox repository mark as processed, message ID. Now, commit transaction. 3. Acknowledge message to message broker only after successful commit. Message broker acknowledge, received message. Catch unique constraint violation exception. Message already processed, duplicate. Leginfo, duplicate message received plus messaged plus. Skipping business logic. Rollback transaction, ensure no partial state. 3. Still acknowledge message to message broker. Message broker acknowledge, received message. Catch exception as E. Some other error during processing. Log and potentially NACK, negative acknowledge. Loaderer, error processing message, plus messaged plus e-message. Rollback transaction. Optionally, NACK to broker for redelivery, or move to DLQ. Message broker NAC, received message. Consumer considerations. Error handling. Implement robust error handling. If the business logic fails before the transaction commits, the message should be rolled back and potentially requeued by the broker for a retry, or moved to a dead letter queue, DLQ. Idempotency beyond the inbox. While the inbox prevents the entire business process from re-executing, ensure that individual steps within the business logic, like deduct stock, are also designed with idempotence in mind, especially if they interact with external systems that don't have an inbox counterpart. Cleanup, similar to the outbox, plan for periodic cleanup of the inbox messages table to manage its size. 6.4 Combining outbox and inbox, a full flow. When both patterns are in place, they provide a reliable, end-to-end asynchronous messaging guarantee. Producer, e.g., order service, business operation, order creation, and outbox message insertion happen in one DB transaction. No matter what happens after commit, the message is durably recorded. Outbox relayer. Picks up message from outbox table. Publishes to message broker. This might involve retries, leading to at least once delivery to broker. Message broker. Ensures message delivery to consumer also at least once. Consumer, e.g., inventory service, receives message. Attempts to insert message ID into inbox table. If successful, executes business logic, e.g., inventory deduction. Both inbox entry and business logic are in one DB transaction. If inbox insert fails due to duplicate ID, business logic is skipped. Only upon successful commit of its local transaction, the consumer acknowledges the message to the broker. This complete flow guarantees that if the originating business operation succeeds, the corresponding downstream business operations will eventually succeed and be applied exactly once, even in the face of network outages, service crashes, and message broker instability. 6.5 Practical tooling and libraries. While the concepts are framework agnostic, various tools and libraries can simplify implementation. Databases. Any relational database with strong transactional support, PostgreSQL, MySQL, SQL Server, is ideal. NoSQL databases like MongoDB or Cassandra can also work if they support atomic operations for multi-document writes or offer eventual consistency models that align with your needs. Message brokers. Kafka, with its log-based approach and CDC integration, is a popular choice. Others include RabbitMQ, Amazon SQS SNS, Azure Service Bus, Redis Streams, etc. CDC tools. Debezium for Kafka integration, Flink CDC connectors, Maxwell's Daemon for MySQL. Framework-specific helpers. Some frameworks or libraries have plugins or dedicated modules that abstract away some outbox-inbox boilerplate, though often a custom implementation gives more control. Implementing these patterns requires careful attention to detail and robust error handling. However, the investment pays off significantly in terms of system reliability, data consistency, and peace of mind in complex distributed environments. In the next chapter, we will expand on these practical considerations, discussing advanced topics like scalability, performance optimization, and effective monitoring. Chapter 7. Advanced topics. Scalability, performance, and monitoring. By now, you understand the fundamental mechanics of the outbox and inbox patterns and their basic implementation. These patterns provide an excellent foundation for reliable messaging. However, as systems grow in scale, handle higher throughput, and become more critical to business operations, a deeper dive into scalability, performance optimization, and robust monitoring becomes essential. This chapter explores these advanced considerations. 7.1 Scalability and Performance Optimization. While the outbox and inbox patterns themselves leverage the local database's scalability, missteps in implementation can lead to bottlenecks. 7.1.1 Optimizing the outbox relayer. The outbox relayer is a critical component for outbound message flow. Batching messages. Instead of fetching and publishing messages one by one, the relayer should always fetch and process messages in batches. This significantly reduces database round trips and network overhead when publishing to the message broker. Adjust batch sizes based on your message volume and typical message size. Efficient queries. Ensure your outbox table includes appropriate indexes, e.g., on a curridat or processedat is null, to make fetching unsent messages fast. Concurrent relayers, polling relayers. Running multiple instances of the polling relayer can increase throughput. However, careful coordination is required to prevent multiple relayer instances from trying to process the same message simultaneously. Techniques like optimistic locking, update, where processedat is null, pessimistic locking, select for update skip locked, or distributed locks, e.g., redes mutex, are essential. CDC relayers. CDC tools like Debezium are inherently designed for high throughput and can often scale independently. The scalability here primarily relies on the message broker's ability to handle the ingested volume. Database cleanup. The outbox table can grow unbounded. Implement a separate background process or recurring job to periodically clean up messages that have been successfully published. This can be done by hard deletion, physically removing older processed messages. This is common for high-volume scenarios. Soft deletion archiving, moving messages to an archive table or simply marking them with a deleted at timestamp. This retains historical data for auditing or potential reprocessing needs. Choose an appropriate retention policy, e.g., 7 days, 30 days, based on auditing requirements and operational needs. Optimizing insert versus update for relayer. When marking messages as processed, an update on the processedit column, soft delete, might be faster than a delete operation, especially if the delete needs to cascade across indexes or be part of a larger transaction. However, the outbox messages table size will grow unless actively managed. 7.1.2 Optimizing the inbox consumer. The inbox pattern involves inserting records and performing business logic in a transaction. Efficient unique constraint check. Ensure your message aid column in the inbox table is the primary key or has a unique index. The database's ability to quickly check this constraint is paramount for deduplication performance. Batch processing, consumer side. While outbox relayer benefits from batching messages out, consumers typically process messages one by one from the message broker to ensure transactional integrity per message. However, consider if your business logic can safely batch operations after the inbox check has passed for each individual message. This is highly dependent on your specific application and data dependencies. Indexing on processedat. For cleanup processes, indexing the processedat column in the inbox table will speed up queries for old messages to be deleted. Cleanup strategy. Similar to the outbox, plan for periodic cleanup of the inbox messages table to prevent it from becoming a performance bottleneck and consuming excessive storage. The message aid is sufficient for deduplication. The full message payload is not needed long-term. 7.1.3 Database considerations. The application's local database is the single point of truth for both patterns and thus a potential bottleneck, if not properly sized and tuned. Database sizing. Ensure your database server, CPU, RAM, IOPS, is adequately provisioned for the combined load of your application's business logic, outbox-inbox inserts, and relayer polling, if applicable. IOPS. Disk I/O operations per second, IOPS, are critical, especially during peak load, as both patterns involve constant disk writes for transactional durability. Connection pooling. Use efficient database connection pooling to minimize the overhead of opening and closing database connections. Transaction log, WAL. For CDC-based Outbox, the database's transaction log, write-ahead log, is heavily utilized. Ensure it's configured for optimal performance and size to accommodate the CDC tool's reading. 7.2 Monitoring and Alerting. Effective monitoring is critical for operating systems that rely on inbox and outbox patterns. You need to know not only if your services are up, but also if messages are flowing reliably. 7.2.1 Key metrics to monitor for Outbox. Outbox queue length, metric. Count of messages in the Outbox table that are processed at is null. Alert. Alert if this number exceeds a threshold, e.g., 100, 1,000 messages for a prolonged period. This indicates the relayer is falling behind or has stopped. Message age in Outbox, metric. Age of the oldest unsent message, i.e. now, min occurred at, where processed at is null. Alert. Alert if the oldest message is beyond a certain time threshold, e.g., 5 seconds, 1 minute. This directly measures delivery latency due to the Outbox. Relayer throughput, metric. Number of messages processed published by the relayer per second minute. Insight helps understand the relayer's capacity and detect drops in performance. Relayer errors, metric. Count of errors encountered by the relayer, e.g., failed to publish to broker, database errors. Alert, critical alert for any sustained error rate. Database write throughput Outbox table, metric. Number of insert operations on the Outbox messages table. Insight indicates the rate at which your application is generating events. Message broker metrics. Monitor the health of your target message broker, e.g., Kafka topic lag, broker availability, producer-consumer throughput. 7.2.2 Key metrics to monitor for inbox. Inbox processing latency, metric. Time taken from receive at to process at for messages in the inbox table. Alert. Alert if this latency exceeds business-defined thresholds. Duplicate message count, metric. Identify attempts to insert into the inbox table that result in a unique constraint violation. This confirms your inbox pattern is handling duplicates. Insight. High counts might indicate a highly duplicated stream from the producer, which could signify issues with the producer's Outbox relayer or the message broker. Inbox queue length, if applicable. Metric. Lag on the consumer group for the source message broker. Alert. Critical alert if the consumer is falling behind its message broker queue. Consumer processing errors, metric. Count of errors in the consumer's business logic or failures to commit the inbox transaction. Alert, critical alert. These messages might end up in a DL queue. Database write throughput, inbox table, metric. Number of insert and update operations on the inbox messages table. Insight indicates the rate at which your application is consuming events. 7.2.3 General monitoring practices. Distributed tracing. Implement distributed tracing, e.g., OpenTelemetry, Zipkin, Jaeger, to trace the flow of a single logical message from the producer through its Outbox to the message broker and into the consumer's inbox, including the business logic processing. This is invaluable for debugging latency and failures. Structured logging. Ensure all components log relevant information in a structured format, JSON, to facilitate easy aggregation and analysis in a centralized logging system. Alerting on trends. Beyond absolute thresholds, alert on trends, e.g., Outbox queue length has been steadily increasing for the past 5 minutes. Dashboards. Create intuitive dashboards in your monitoring tool, Grafana, Datadog, etc., that provide a quick overview of message flow, latency, and error rates for both Outbox and Inbox. 7.3 Managing long-running or external dependencies in consumers. Sometimes the business logic within a consumer, part of the inbox transaction, might involve long-running operations or calls to external systems, e.g., a third-party API, a legacy system. Incorporating these directly into the inbox transaction has risks. Transaction timeout. Long-running operations can cause the database transaction to time out, leading to rollback and message reprocessing that might involve repeated calls to the external system. Idempotency challenges. Ensuring idempotency with external systems can be harder if you don't control them. Blocking. If the external system is slow or unavailable, it blocks the consumer's ability to process other messages. Strategies for external dependencies. Move external calls outside the transaction. If the external call is truly a side effect that can be eventually consistent and retried independently, perform it after the inbox transaction has committed. If it fails, the consumer can retry just the external call later. This means you might need to reconsider the entire transaction committed, part of the inbox pattern for these specific side effects. Compensating transactions/saga pattern. For complex business processes that span multiple services and external systems, the saga pattern, which we'll discuss in Chapter 9, offers a more robust framework. A saga breaks down a large transaction into a sequence of smaller, local transactions, each with its own compensating action in case of failure. The inbox pattern is still a fundamental building block within each local transaction of a saga. Asynchronous external calls. Use asynchronous communication for external calls, perhaps by putting another message on a dedicated queue for the external system. The consumer services simply pushes the message, and another component handles the external interaction, maintaining a clear separation of concerns, ensuring local atomicity with Inbox-Outbox, and then strategically integrating with external systems using other patterns like sagas or robust retry mechanisms, is key to building highly available and consistent distributed systems. In the next chapter, we'll ground these concepts further by exploring real-world applications and case studies where inbox and outbox patterns have been successfully deployed. Chapter 8. Real-world applications and case studies. The inbox and outbox patterns are not merely theoretical constructs. They are battle-tested solutions deployed across a vast array of industries and system architectures. This chapter will explore various real-world scenarios where these patterns prove invaluable, offering practical insight into their application and the problems they solve. 8.1 E-commerce transaction processing. One of the most archetypal use cases for reliable messaging patterns is e-commerce. Consider the workflow of an online order. Scenario. A customer places an order on an e-commerce website. This single action triggers multiple downstream events. Services involved: order service manages customer orders. Inventory service tracks product stock levels. Payment service processes payments and updates billing information. Shipping service handles delivery logistics. Notification service sends confirmation emails SMS. Problem without outbox inbox. If the order service simply saves the order to its database and then tries to send messages to other services, it faces the atomicity gap. An order could be saved, but messages lost, leading to customer charged, but item not reserved or shipped. Inventory not updated, leading to overselling. No confirmations sent to the customer. Solution with outbox and inbox. Order service, producer outbox. When an order is placed, the order service begins a local database transaction. It saves the new order record to its orders table. It inserts an order placed message containing order ID, items, customer info, etc. into its outbox messages table. The transaction commits. An outbox relayer then picks up the order placed message and reliably sends it to the central message broker, e.g., Kafka topic, e-commerce orders. Inventory service consumer inbox subscribes to e-commerce orders topic. When it receives an order placed message, it starts a local database transaction. It attempts to insert the message's unique message ID into its inbox messages table. If the ID is new, it proceeds to deduct the ordered items from its product inventory table. The transaction commits, and the message is acknowledged to the broker. If the ID is a duplicate, the transaction rolls back, and no stock is deducted twice. Payment service, consumer inbox-outbox, subscribes to e-commerce orders topic. Processes the order placed message using its inbox to ensure idempotency. If the payment logic is external, e.g., calling a third-party payment gateway, it might internally use an outbox pattern again to publish a payment requested message to a different internal queue, which a payment processor picks up. Once the external payment is confirmed, The payment service could then publish a payment processed message, again, via Outbox, for other services to consume. Shipping service, consumer inbox, subscribes to payment processed and potentially order placed messages, uses inbox to log and deduplicate, updates shipping status and prepares for dispatch. Notification service, consumer inbox, subscribes to order placed and payment processed messages, uses inbox to prevent duplicate notifications, sends confirmation emails, SMS. Benefit: this architecture ensures that even if the message broker is temporarily down or a particular service experiences failure, the core business action, order placement, is durable, and all necessary downstream actions are eventually processed once and only once from a business perspective. 8.2 Financial Trading Systems. In financial services, even minor inconsistencies can lead to significant financial losses. High transaction volumes and strict consistency requirements make reliable messaging paramount. Scenario: a trading system processes a trade order, which must update customer portfolios, calculate commissions, and notify regulatory bodies. Services involved: trading service initiates and processes trade orders. Portfolio service manages customer holdings. Commission service calculates and applies fees. Compliance service logs trades for regulatory reporting. Problem without Outbox inbox. A trade order logged in the trading services database might not be reflected in a customer's portfolio or could be reported multiple times, resulting in incorrect financial statements or regulatory fines. Solution with Outbox and Inbox. Trading service producer Outbox completes trade order data in its database. Inserts trade executed message into its Outbox, including unique trade ID, order details, and execution price. Outbox relayer publishes to message broker. Portfolio service, consumer inbox, receives trade executed message, uses inbox to process only once. Updates customers' portfolio holdings and cash balance. Commission service, consumer inbox, receives trade executed message, uses inbox, calculates commission and updates billing records. Compliance service, consumer inbox, receives trade executed message, uses inbox to ensure correct filing. Logs trade details for audit and compliance. Benefit: the patterns prevent data loss, ensures that financial calculations are accurate, and that regulatory reporting is precise, avoiding costly errors and penalties. 8.3 IoT data ingestion and processing. Internet of Things, IoT. Devices generate massive streams of data, sensor readings, device status, location updates. Processing this data reliably and reactively is crucial. Scenario: smart home devices send telemetry data, temperature, humidity, motion detected, to a central platform for analysis and triggering actions. Services involved: device gateway ingests raw device data. Telemetry processing service cleans, validates, and stores telemetry. Rule engine service evaluates data against user-defined rules, e.g., if temperature 25 degrees C, turn on fan. Notification service sends alerts. Problem without Outbox inbox. Raw telemetry from a device might be persisted, but the command to turn on a fan might be missed or sent multiple times, leading to device malfunction or user frustration. Solution with Outbox and Inbox. Device gateway, producer Outbox, receives raw device telemetry. Persists raw data to its local data store, e.g., time series DB. Pushes an telemetry event message using Outbox, containing device ID, timestamp, and readings. Outbox relayer sends to message broker. Telemetry processing service, consumer inbox, receives telemetry event. Uses inbox, performs data cleaning, enrichment, and stores processed telemetry into a long-term analytical store. Rule engine service, consumer inbox Outbox, receives telemetry event or processed data from telemetry processing service. Uses inbox, evaluates rules. If a rule is triggered, e.g., temperature exceeds threshold, it uses its own Outbox to publish a device command message, e.g., turn on fan. Device command service, consumer inbox, receives device command message, uses inbox to ensure command is executed only once, sends actual command to device. Benefit: ensures that device data is reliably captured and processed, and commands are sent and executed correctly, preventing data loss and erroneous device behavior. 8.4 User provisioning and identity management. When a new user signs up for a service, multiple actions must happen across different systems to correctly provision their account and access. Scenario: a new user signs up for a SaaS platform. Their user account needs to be created, billing setup triggered, and access rights configured across various modules. Services involved: user management service, handles user registration and profile management. Billing service, manages subscriptions and invoicing. Access control service, assigns roles and permissions. CRM integration service, syncs user data to the CRM. Problem without Outbox Inbox. A new user might be created in the user management service, but their billing subscription might be missed, or they might not get the correct access rights, or their data could be synced multiple times to the CRM. Solution with Outbox and Inbox. User management service, producer Outbox, registers new user in its database. Inserts user-registered message into its Outbox, including user ID, email, and subscription tier. Outbox relayer publishes to message broker. Billing service, consumer Inbox, receives user-registered message, uses Inbox, creates a new billing account subscription for the user. If this involves external payment gateway, it might use its own Outbox for billing profile-created messages. Access control service, consumer Inbox, receives user-registered message, uses Inbox, assigns default roles and permissions to the new user. CRM integration service, consumer Inbox, receives user-registered message, uses Inbox, creates or updates the user's record in the CRM system. Benefit: ensures that new users are consistently provisioned across all necessary systems, reducing manual intervention and preventing service access issues or billing discrepancies. These case studies highlight the versatility and criticality of the inbox and outbox patterns. They provide a systematic approach to building robust, consistent, and resilient distributed systems across a wide range of domains, from high-volume financial transactions to real-time IoT data processing and foundational user management. They empower developers to confidently achieve, exactly once, processing semantics at the business level, even when relying on message brokers that only guarantee, at least once, delivery. In our final chapters, we will look beyond just inbox and outbox, explore related patterns that complement them, discuss emerging trends, and offer some concluding thoughts on building resilient systems with confidence. Chapter 9, Beyond Inbox Outbox, Related Patterns and Future Trends. The inbox and outbox patterns are incredibly powerful tools for achieving reliable message delivery and consumption in distributed systems. However, they are building blocks, not a complete solution for every distributed consistency challenge. This chapter explores related architectural patterns that often complement or build upon inbox and outbox, and briefly looks at future trends in this evolving space. 9.1 Complementary Patterns. While inbox and outbox ensure atomicity between local database transactions and external message queues, complex business processes span multiple services and may require more advanced coordination. 9.1.1 Saga Pattern. The saga pattern is perhaps the most significant complementary pattern to inbox and outbox. A saga manages a long-running business transaction that involves multiple services, with each service performing a local atomic transaction, often using the outbox pattern, and publishing an event. If a step in the saga fails, compensatory transactions are executed to undo the changes made by preceding successful steps, maintaining overall data consistency. How it works with inbox-outbox. Each local transaction within a saga, e.g., reserve inventory, process payment, ship order, would use the outbox pattern to atomically commit its database changes and publish an event signaling its outcome, e.g., inventory reserved, payment failed. The saga orchestrator or choreographer would then consume these events, using the inbox pattern to ensure idempotent processing, to decide the next step, or to trigger compensating actions. Example: an order process that spans inventory, payment, and shipping services. Orchestrator sends reserve inventory command. Inventory service, using Outbox, reserves inventory within its local transaction. Publishes inventory reserved event. Orchestrator, using Inbox, receives inventory reserved event. Sends process payment command. Payment service, using Outbox, processes payment within its local transaction. Publishes payment processed event. Orchestrator, using Inbox, receives payment processed event. Sends ship order command. Shipping service, using Outbox, records shipment within its local transaction. Publishes order shipped event. Saga complete, what if payment fails? Payment service, using Outbox, publishes payment failed event. Orchestrator, using Inbox, receives payment failed event. Orchestrator sends release inventory, compensating command to inventory service. Inventory service, using Outbox, releases inventory, publishes inventory released event. Orchestrator receives inventory released, closes Saga. The Outbox pattern ensures the outcome of each local transaction is reliably propagated, and the Inbox pattern ensures the orchestrator, or other services in a choreographed saga, reliably processes these events, preventing double compensation or missteps. 9.1.2 Command Query Responsibility Segregation, CQRS. CQRS is an architectural pattern that separates the responsibility of handling commands, requests that change state, from queries, requests that read state. Commands go through a command handler, which applies changes to the right model. This typically involves an Outbox event signaling the change. Queries, read from a separate, often optimized read model. How it works with Inbox Outbox. When a command is executed and modifies the right model, e.g., updating a user's address, the Outbox pattern ensures that a corresponding user address updated event is atomically captured and published. Other services, particularly those responsible for updating read models, would then consume this event using the Inbox pattern to update their denormalized views for efficient querying. Example: a user write service updates user data and uses the Outbox to publish user updated events. A user read service consumes these events via its inbox and updates its highly optimized read-only user profile database. 9.1.3 Event Sourcing. Event sourcing is an architectural pattern where the state of an application is not stored as a single, current snapshot, but rather as a sequence of immutable events representing every change that has ever occurred. How it works with Inbox Outbox. When an event-sourced aggregate, e.g., an order aggregate, receives a command, it validates the command, generates new events, e.g., order placed, order items updated, and stores these events in an event store. The act of persisting these new events to the event store, which is essentially a database with specific characteristics, can be combined with the Outbox pattern to also publish these events to a message broker for other services to consume. Example: an order aggregate receives place order command. It generates order placed event. It persists order placed event to its event store. Simultaneously, via the Outbox pattern, it also publishes order placed event to the message broker. Other services consume this using Inbox. 9.2 Limitations and when not to use Inbox Outbox. While powerful, Inbox Outbox are not a panacea. Synchronous operations. They don't solve synchronous, near real-time consistency problems. If you need immediate consistency across services for a single user interaction, e.g., a reserve booth operation that must guarantee immediate, global uniqueness, you might still need distributed locks or rethink your consistency model. Cross-database referential integrity. If your application must maintain strict referential integrity across multiple databases that are owned by different services, e.g., foreign key constraints across microservices, Inbox Outbox with eventual consistency might not be sufficient. This typically indicates a lack of true service boundary separation. Overhead for simple cases. For very low volume, non-critical, or simple interactions where fire and forget is acceptable and occasional message loss is tolerable, the overhead of managing Outbox inbox tables and relayers might be overkill. Shared database anti-pattern. While an inbox-outbox solution uses a local database for each service, it does not reintroduce the anti-pattern of having multiple services share a single database to achieve consistency. Each service still owns its data. 9.3 Future Trends in Reliable Distributed Messaging. The landscape of distributed systems is constantly evolving. Here's a glimpse of trends that might influence future approaches to reliable messaging. Managed services and serverless. Cloud providers are increasingly offering managed services that abstract away the complexities of message brokers and even provide built-in patterns for reliable processing. Serverless functions paired with event sources simplify deployment and scaling, but developers still need to explicitly design for idempotence and event ordering. Streaming platforms as the core. Platforms like Apache Kafka are becoming central nervous systems for entire enterprises, acting as durable event logs beyond just message queues. This strengthens the case for CDC-based outbox patterns. Unified development experiences. Frameworks and platforms that provide more integrated and opinionated ways to build event-driven microservices, potentially embedding inbox-outbox capabilities and Saga orchestration directly into their programming models, will gain traction. Advanced consistency models. Research continues into stronger consistency models that offer better guarantees with less operational overhead than traditional 2PC, while still being more flexible than eventual consistency for certain domains. Observability and AIOps. As distributed systems grow in complexity, advanced observability tools, coupled with artificial intelligence for IT operations, AIOps, will become crucial for detecting, diagnosing, and even predicting issues in message flow and consistency. Automated remediation for common failure scenarios will also become more prevalent. Declarative event flow. Moving towards more declarative ways to define event flows and business processes, allowing tools to generate the underlying messaging infrastructure and reliability patterns automatically. While new technologies and approaches emerge, the fundamental problems of distributed systems, network unreliability, partial failures, and the need for consistency remain. The inbox and outbox patterns, built on solid principles of local transactional integrity and asynchronous communication, will likely continue to be foundational building blocks for building robust, fault-tolerant applications for the foreseeable future. They serve as a testament to the power of thoughtful architectural design in overcoming inherent distributed challenges. Chapter 10. Conclusion: Building Resilient Systems with Confidence. We have journeyed through the intricate world of distributed systems, dissecting their inherent challenges and the critical role of reliable messaging. From the pitfalls of asynchronous communication to the elegant simplicity of the inbox and outbox patterns, we've explored how these battle-tested solutions empower developers, architects, and technical leaders to build truly resilient systems in the face of uncertainty. The problem we solved, the core problem addressed by this book, is the atomicity gap, the critical disconnect between a service's local database transaction and its external message communication. In distributed architectures, simply committing data to a database and then attempting to send a message externally is a recipe for data inconsistencies, lost business events, and operational nightmares. While traditional distributed transactions, like two-phase commit, exist, their significant performance overhead, single points of failure, and tight coupling render them largely unsuitable for modern, scalable microservices environments. The patterns that provide the solution. The outbox pattern is the cornerstone of reliable outbound messaging. By committing the intention to send a message to a local database within the same atomic transaction as the business data, it guarantees that if the business operation succeeds, the message will eventually be sent. This pattern shifts the responsibility of message durability from the message broker to the service's own database, making the producer resilient to broker downtime and network glitches. The inbox pattern complements the outbox by ensuring that messages are processed exactly once from a business perspective on the consumer side. Even when the message broker delivers them multiple times, an inherent characteristic of at least once delivery guarantees. By recording each received message's unique identifier in a local database transaction, The inbox pattern enables robust duplication detection and prevents unintended side effects. Together, these patterns form a powerful duo, allowing services to confidently engage in asynchronous communication, knowing that their business operations will remain consistent and their messages will be accurately delivered and processed across the distributed landscape. A foundation for resilience, the adoption of inbox and outbox patterns fundamentally changes the mindset of building distributed applications, embracing eventual consistency. While they enable strong consistency within local transactions, the patterns also lean into the reality of eventual consistency across services. They guarantee that all necessary operations will eventually happen, even if not instantaneously. Decoupling and autonomy. They champion the principles of microservices by allowing services to remain highly decoupled and independently deployable. Services primarily rely on their local database and the guarantee of the message transport instead of synchronous, cross-service transactions. Operational confidence. By building in reliability from the ground up, these patterns significantly reduce the likelihood of costly data synchronization issues, lost business processes, and the associated debugging headaches, leading to more stable production environments. Beyond the basics, practicality and best practices, we've covered not just the what and why, but also the how. Implementation choices. From straightforward polling-based outbox relayers to more advanced change data capture, CDC mechanisms, we explored the practicalities and trade-offs of different implementation strategies. Scalability and performance. The discussion extended to optimizing database interactions, managing table sizes, and leveraging techniques like batching and concurrency to handle high message volumes. Monitoring and alerting. Crucially, we outlined the specific metrics and dashboards necessary to gain visibility into the health and flow of your message pipelines, enabling proactive identification and resolution of issues. Complementary patterns. We briefly touched upon how inbox and outbox serve as building blocks for more complex patterns like Saga and CQRS, which tackle long-running business processes and query optimization respectively. The journey continues. The world of distributed systems is dynamic, continuously evolving with new technologies and refined best practices. While our focus has been on the foundational inbox and outbox patterns, the core principles of designing for reliability, handling failures gracefully, and ensuring data consistency will remain timeless. As you embark on or continue your journey in building distributed systems, remember these key takeaways. Acknowledge the network. Always assume the network is unreliable, latency is not zero, and services can fail independently. Design your systems with these realities in mind. Transactions are local. Leverage the power of local database transactions for atomicity, and use patterns like inbox and outbox to reliably bridge the gap to external communication. Idempotence is non-negotiable. Design your consumers to handle duplicate messages without unintended side effects. It is your strongest defense against the realities of at least once delivery. Observe and iterate. Implement comprehensive monitoring and tracing, and be prepared to iterate on your designs as your system scales and user demands evolve. By internalizing these principles and effectively applying patterns like inbox and outbox, you are not just building software. You are crafting robust, resilient, and trustworthy distributed systems. You are empowering your organization to operate with greater confidence, deliver seamless user experiences, and confidently navigate the complexities of the modern digital landscape. May your messages flow reliably, and your systems always remain consistent.